Salam sejahtera. I'm Siah Yih Hoong from UNIMED. So today I'm going to present my title, which is Developments of Camshaft Ventilators Mechanism in Medical Applications for Ereka 2024. Okay, so let's start. Okay, so these presentations consist of few elements, which is introductions, literature review, methodology, discussion result, and conclusions. Okay, so before I start my presentations, I would like to have a short brief on what is a camshaft ventilators. So a camshaft ventilators is actually a combination of medical ventilators and a cam and follower mechanism. So that's all. Yeah. Okay, so for this project, we have three objectives. The first is the cam design, which means that this project required us to design a cam profile that can works perfectly. And second objective is to develop an IoT system so that the data from the patients can be monitored by a mobile applications in a long distance. And the third one is also the last one is to develop a control systems for the motors for the ventilator systems. Okay, so we have three problem statement as well. So the first problem statement is the cost effective. Okay, so according to Malaysia now, Malaysia lost 30 million just to purchase 136 ventilators. So it seems that a single unit of ventilators is really expensive, and Malaysia is already facing limited budget of purchasing ventilators. And the second issue is the accuracy problem. So this research shows that some home ventilators are quite inaccurate in delivering the preset tidal volume. So this is probably caused by the patient's conditions. It may not always be stable, and also the mechanical parameters may not be constant. And the third issue is the monitoring issues. So for traditional ventilators, right? So medical teams would keep visits the patients to get the data from the ventilators. So this problem probably can be solved by applying IoT systems. So the medical teams can be directly get the data from the mobile applications. Okay, so in order for us to classify the medical ventilators, we have two ways. The first way is by the power systems. The second way is by the applying methods. So we have two power systems, which is pneumatic and electrical. So as this diagram shows, double circuit pneumatic ventilator, which is powered by pneumatic. So we can observe that they have two airway. The first airway is delivering compressed air so that it can compress the bag inside the bottles. And the second airway is delivering the oxygens where to the patients whenever the bag inside is being compressed by the compressed air. So for this diagram, it shows single circuit pneumatic ventilators. So the tidal volumes can be delivered by the patients by manipulating the valve right here. Yeah. So for the electrical ones, it always have a mechanical mechanisms on the ambu bag. So they will work together and deliver the tidal volumes to the patients. If we classify by the applying methods, we have non-invasive ventilations and invasive ventilations. The non-invasive ventilations would require the patient to wear a mask. However, an invasive ventilations will require the patient insert a tube inside the lung airway. So for us to design the cam profile, we have to study about the three basic waveforms for the ventilations because the cam design is really dependent on the waveform. So here it is. So this is the pressure waveform. We have also the flow waveforms, and also we have the volume waveform. For your informations, traditional ventilators actually controlled by two modes. The first mode is the pressure. The second mode is the volume. So if we control by volume, means that we are going to manipulating the volume and send to the patients. If we control the ventilators by pressure, we will going to manipulate with the air pressures and send the air towards the patients. So in this project, we applying a volume controlling methods for these ventilators. So it is known as volume control ventilators. And this is the core of the whole project, the CAM mechanisms. A CAM mechanisms actually consists of CAM and the followers. So we can notice that the cam is rotating right. You rotate, and then it push the followers up and down, up and down. So in another word, it is said that the cam convert the rotatory motions into linear motions. So we have several shapes or types of cams. We have plate, wedge, barrel, and face. So each of them have their own um motions. So for the plate cam, it rotates. For the wedge cam, it have such motion. Barrel cam and face cam have another motions. Definitely, we will have different types for the followers. So we have roller followers, we have flat face followers, we have knife edge, we have curved shoes. And each of them have their own benefits and also their advantages. So in this project, a roller followers and also plate cam is used, okay? Is applied in this project. So this is the displacement time graph. So this is actually a call for how we convert the volume waveform into the waveform that we design our cam profile. Okay, so it consists of four elements: the lift, the rise, the dwell, and the returns. The rise and the returns are the positive and the negative of the displacements of the followers, while the dwell is actually means whenever the followers is stopped or maintained at a certain displacement or a certain distance, it is known as dwell. So the lift is the total displacement of the followers displaced. Okay. Okay, so for this project, it's separated into two sessions. The first sessions will be mainly focused on cam design, and the second sessions will be mainly focused on the mobile app developments, the control design, so the control system design, and also the product design. Okay. So this is the system block diagram. We have input, process, output elements. For the input element, we have power source, sensors, push button. For the output element, we have motor, OLED displays, mobile applications. And for the process elements, we have Arduino Mega, ESP32, cloud monitoring systems. And Firebase will be used for cloud monitoring systems. So this is a graphical view. So it's more beautiful. Yeah. Okay, so this slide is showing the component used in my project. Okay, the second column shows the component and the rest one is the budget. So this project actually cost 700, around 700, and it is really cheap compared to an actual ventilator that costs around 10,000 or 5,000. But there's one thing I must say because um the expensive one have their own benefits and the cheap one will have their own disadvantages. Yeah, that is the logic and that is the truth. Okay, so we're going to see the methodology for the system workflow. So these ventilators operate by settings, by push button. What going to be set? The parameters for breathing periods is going to set by the push buttons, and whenever it is set, the motor will start to rotate with the periods set before, and then the sensor will start to measuring the data from the patient and send the data to the real-time database. And then we can achieve the real-time monitoring. So this is a system workflow. It is quite similar with the previous slide, just that we add some things right here, which is threshold condition triggered. So this means that if the patients trigger some threshold conditions like have a lower heart rate or lower oxygen levels, the alarm system will be triggered. Okay, and it is triggered by mobile app. Okay, which means the mobile app will notify the user with a notifications that saying, hey, your parent is in abnormal stages, something like that. Okay, so this is the circuit design. We can see that this is a transformer, this is the motor driver, this is the Arduino Mega, this is a ESP32, this is a NEMA 17 stepper motor, this is the Max 30102 pulse and oximeter, this is the OLED, this is the pressure sensor HX710B, and this two is the push button. Okay, so this is the front view and this is the isometric view of my prototype design. So we can see that we applying, also this project applying a plate cam and a roller followers. And I actually added a leverage system right there because it will greatly reduce the force required to push down the followers. Okay. Yeah. So this side will be the valve, in and out air valve. Okay, so this is the ventilations waveform design. So according to Protofy.xyz, which is also a developers of a camshaft ventilators, okay, they develops their cam profile by using gamma regressions. However, they found that there is some disadvantages because the curves is slightly lack of flexibility. So they suggest us to use a Bezier curve instead. So the difference of Bezier curve and gamma regression is shown in this slide. So this is the gamma regressions and this is the Bezier curve. Yeah, the Protofy.xyz also said that the curve of the ventilators or the ventilation waveform is actually in form of a piecewise function. So it will be a combination of different uh, graph or different curves. So this is the second order Bezier curve. We have 3 points, the starting point, ending point, and a control point. So wherever the control point is, the curvatures of this line will always tend to curve towards the control point. So imagine that I have a control point at here. So it will curve towards here and rotates to the ending point. Yeah. Okay, so all of the parameters is taken from the medical book named as Essentials of Mechanical Ventilations. Okay, so this is the formulas to calculate the Bezier curves. And also, this is the piecewise functions that I mentioned earlier. So this is the straight line equations used for inspiratory phase and the Bezier curve equations or Bezier curve used for expiratory phase. And the cross one is the control point of the Bezier curves. Okay. So by combining them together, we will get the ventilations, volume control ventilations waveform. So if compared to something like this, okay, it's quite identical, right? Okay. So in order to smooth the breathing time to have a more steady breathing rate, okay, we will have to add some delay times among the cycles. So if there are no delay time, the patients will immediately breathe in and breathe out, breathe in and breathe out like something like asthma. Okay. So we don't want that. Okay. We add some delay times so that it will have a probably slow and steady breathing process. Okay. So after we get these curves, right, the waveforms, right, so it will be converted into a polar coordinates. Okay. So the polar coordinates again will convert into a Cartesians. So we can get the x locations, y locations of this design, and it will be the cam profile design. Okay. So for the control systems for the motors of the ventilation systems, okay, it will have this or such formulas. Why? Because we know that if we wanted to control the stepper motors by Arduino Megas, they always make use of microstep per second to control the speed, right? However, we want to control it by setting how many periods of the patient is breathing. So we have to derive these formulas, okay, and then it will become an open loop controls for the motor. Okay, so we set how many periods and then it will automatically calculated, converted into microstep per second and sent to Arduino Mega, and also the stepper motor will rotate as what periods is being set up. Okay, so after that, we're going to enter the result and discussions. Okay, so the design is being exported into SolidWorks, and a few analysis is being carried. So motion analysis. So this motion analysis shows 0% error. Hold on, 0% difference because we are still in simulation. Okay, and this 0% difference can only prove that our theory is correct so that we can develop a MATLAB standalone desktop applications to generate another cam profile. So if we want to generate a new cam profiles, right, we can just directly enter how the parameters like the respiratory time, the tidal volumes, and the min cam radius. So that's all. So we don't need to reconfigure the programming language again. I mean, like the coding again. So we can just directly double click the apps and then enter the parameters, click generate and save the Excel file and import to the SolidWorks, and there will be automatically 3D design at there. Okay. So for actual ventilators, right, they use flow sensors. Okay. Their flow sensors cost around 200 to 300 Malaysian ringgit. So because of I want to cut down my cost or save a bit budget, so I come up with a new idea which by using Bernoulli equations. So we know that Bernoulli equations is used for gas flows, fluid flows, right? So we can apply it. So the Bernoulli equations have these formulas, okay? We can derive it to get the flow and also get the volume. So the flow multiplied by time, we will get the volume of air delivered to the patient at that moment. So it is said that it is a tidal volume. So if we analyze in real life, so we will have percentage difference shows right here and the graph. So the graph is actually quite identical with the theoretical one. But if we look carefully at the percentage difference, we have 100 percentage difference. But hold on, this is not means that this is not means that the ventilators is not accurate at all. Just that we have to look at the actual value of the theoretical value, because of they have zero theoretical values. I mean the theoretical values is zero and the actual value is 1.86. It only exceeded a bit, but since it is compared to zero, so there will be 100% percentage difference. So this percentage difference is probably cause of the airtight systems, which means probably there's some leakage on a valve, on a pipe, or on the pressure sensors like that. Okay, so don't worry, that's just a normal air leakage and cause a small error. And this is the results from the motors. Okay, the motor value analysis is compared or analyzed by comparing the actual motor periods with the motor periods from coding, which means if we want to rotate the motors, right, so we set 2-second period, and the 2-second period will be converted into SPS by the formulas that I mentioned above, and then it will start to rotate the motors. And whenever the motor is rotated, okay, it is being recorded and recorded by a digital timer. Okay, so we can record the data. So that the percentage difference is calculated from comparing these two columns. Okay, and this graph shows that the faster the motors rotates, right, or the shorter the periods of the motor, there will be a higher percentage difference. So this is probably due to the inertia of the motor. When the motor rotates faster, it will start to lose a bit control of it. So we can see that if we rotate if we rotate slower, the percentage difference is lower. However, this is just an assumption only. Okay, for the max 30102 pulse and oximeter analysis, it is compared by an actual pulse and oximeter that available on the market. Okay, so this is the percentage difference. Okay, so we can observe that the percentage difference for the pulse or for oxygen levels having irregular patterns, graph patterns. Okay, so it can be said that this difference is caused by model difference. Okay, so it is not dependent on, or the higher the BPM, okay, the higher the percentage error. No, this is caused by model difference, hardware difference. Okay. And this is the mobile applications that allow the user to monitor patients' data in long range. So it allow user to register the profile, log in the profile, and it will shows the main page. So it will shows the name and the ventilator's ID, the respiration period, which means the motorcycle, and the heart rate and the SpO2. And this is the graph. So we have two buttons. The first button is detect, the second button is log out. So if we press detect, it will start to detect. So this is the screenshot of my result. And if we press log out, it will just exit the app. Okay, I mean log out from the account. So if the patient's having abnormal stages, the user will be notified by notifications. That's all. Okay, so this is the Firebase. I mean the real-time database that having a name as Firebase. However, there are some issue with Firebase, but that one is for later. Okay, so in this database, we can see that there are several nodes by their ventilator's ID. So vent 001, the patient name, temp data pack 1, temp data pack 2, ventilator ID. So the node is arranged by ventilator ID because we can know that which patients is using which ventilators. So if I register Ahmad or Ali or anyone with any ventilator ID, so will it will bond the name with the ventilator ID together. So if we check the database, we can know that, oh, this patient is using which ventilators. Okay. So the temp data pack 1 and temp data pack 2 is quite weird because we have ABCDs inside, right? Actually, temp data pack 1 consists of the pulse, the oxygen levels, the motors period, and the temp data pack 2 consists of volume, flow, pressure, and time. Okay. The reason of merging the data together is because of whenever the ESP32 uploading certain data to Firebase real-time database, it seems to have a slight delay. So if we have a long data, like for example, instead of temp data pack 1 and 2, I've made it with volume, flow, pressure, time, or blah, blah, blah. So each node, each branch will have one delay. Okay, so if we have a long branch, we have many branch, we will have a more delay time. So in order to shorten the delay time, the data will be merged together in a data package, and this will greatly reduce the time delay. Okay. So this is the front view. This is the isometric view of my prototype assembly. It's quite identical, right? Just that the wire is a bit messy. Okay, so for the conclusion, the title for this project is develop a camshaft ventilator mechanisms for medical applications. And for the SDG, it relates with good health and well-being, industrial innovation and infrastructures. And for the ventilator control mode will be volume control mode. So along this project, the three objectives is achieved, which is the camshaft profile is successfully designed. Even a MATLAB desktop applications is being developed, right? An open loop control system is successfully designed, which is controlling the motor's rotating speed, and also real-time monitoring app is successfully developed. So it shows that this app successfully monitored, monitor the patient data. Okay. So for conclusions for future improvements, right? Probably we can use a lightweight material because for this prototype assemblies, I'm using wood. Yeah. So if we want to make it more light, we can use lightweight material like acrylic, steel, any kind of thin steel that can handle that is strong enough, and replacing cylinder pump with medically suitable material. Okay, so in this project, right, the pump I'm using is the PVC pipe. So whenever it's how to say, if it's functioning for a longer period of time, definitely it will create debris inside, right? So it is better to replace it with a titanium, which is a medically suitable material. So it will greatly reduce the debris, and also we can probably add some filter inside to filter out the debris. Also, we can add some backup power supply. So if imagine that we have electrical cutoff, so we will have the backup supply to temporarily supply the ventilator. Okay. Or also if we want to go outside with my ventilators or with the ventilators, we can use the battery. Okay. Also, for the cloud monitoring platform, okay. So for the cloud monitoring platform in this project, which is Firebase, okay, it seems to have some delay. For example, after the first 100 data is being uploaded to the Firebase database, the database will lag for a while and then returns to normal. And for another 100 data again, it will lag a while and then continue normal. And it goes vice versa. So probably we can switch another cloud monitoring platform. And also for the HX710B pressure sensors, this pressure sensor is from China's, and it really easily got broken. So if we want to use for long term, it is better to use another pressure sensors that can work for a longer period of time. And it will be, I have to say, more easily to program because this HX710B lack of data sheet. So it is really tough to find a suitable libraries for the HX710B to code it. Okay, so for the demonstration, so initially we can observe that my finger is on the oximeters and it shows 70 ppm and 97.46% of my oxygen level. So it means that my blood pulse per second, okay, beat per minute is being measured, and also the oxygen level. Okay. So this three button will configure the speed of the motor. Yeah. So at this moment, I pressed the wrong button. I actually should press this one. Okay, we reduce the period, so we can notice that the motor spin faster. Okay, and then I'm going to set the period again. It's going to be set into 4 or 5, I think. Okay, 6 seconds. Okay, if we count carefully, 1, 2, 3, 4, 5, 6. It's around 6 lah, because I'm not a stopwatch, right? Definitely I will have some slightly difference. So if you really want to check the actual periods, maybe you can use your phone and open a stopwatch and you can measure it. Okay. Okay, so for this one is the mobile application. So the mobile application's name as event. C means for capture, event means for ventilators, right? Okay. So yeah, this is the C and this is the vent. So I'm logging with the ID and the name. Okay, so yeah, the name is Unimap, the ventilator ID is vent001. And after that, we press detect. So it will start to detect the data. Okay, we can see that it goes smooth. But since there are some problems with the Firebase, so after 100 data, it will get slightly delay or something. So yeah, yeah, this is the alarm. So if we notice, whenever the patient's heart rate is fall below 60, 50, and oxygen level is become 60, wait, sorry, it will it will be it will trigger the alarming systems. Okay. So even if I quit the app, the notification still exists. Okay. So it will keep on ringing until the patient's levels, until the patient's back to normal. And I press log out. So try to log in with a ventilator ID that not exist inside the database. So it will show ventilator ID not exist. So I'm going to register a new one. Okay. Okay, so after I register a new one, I try to log in with invalid patient's name. So it will show invalid credentials, which means I will have to retype the correct name. So, okay, invalid credentials. So if I press, okay, so we will log in back again. So this is my mobile applications and yeah. So this is the end of the presentation. I would like to say thank you. So this is the awards that I get from MDEX achievement. Yeah, thank you. Thank you for patience.